Hi, welcome to Math 150. This is lecture 10. And so what we're going to be doing today is doing a little bit of derivatives, notation, and rules. We'll talk about some examples, maybe some applications if time permits. And then there was a request to do tangent planes. Probably do maybe later in the semester. One of the questions is always, why do we care about studying functions of certain variables? Well, the more variables you have, the more likely you are to be able to model something that you care about. When you only have one variable, it's kind of limiting in terms of the relationships you can have. The difficulty, of course, is the more variables you have, the less likely you are to have something that's tractable. You can get something at the end of the day. All right. So one of the most useful concepts in all of mathematics is the notion of the derivative. So the derivative tells you the instantaneous rate of change of the function at a point. Right, so if we want to understand how a function changes, the derivative helps us. So let's say we have some function. Here's y equals f of x. Here's some point a. Here's f prime of a. And what we can do is we can write down the tangent line at the point a comma f of a. So the tangent line is y minus f of a is f prime of a x minus a, or y is f of a plus f prime of a x minus a, or if you want, f of a plus df dx at point a times x minus a. And hopefully it's clear that I'm writing it pedantically the last way to make this more amenable to generalizations. Start to see and looking at how the function is changing as I move in the x direction. And the idea is, if I stay close to a, this should be a very good approximation to the function. Right. So as an example, can anybody tell me what the square root of 122 is? Yes. Slightly more than 11. How much? Point 1, 0.001. You give me a rough order of magnitude. So maybe on the side of 0.1, I'm moving one whole unit forward. So let's try to come up with a function at a point. So what point do you think I should be near? So I want to try to approximate my function with a tangent line. So I have to figure out, first of all, what is my function of x? It's very easy if I give you the function and say use the tangent line to approximate this. I'm making it a little bit harder now. I'm not giving you the function. I want a function. What topics? I know at a, it should be easy to find f of a and approximate near a by the tangent line. So what do you think the function might be? F of x is so we could try f of x equals the square root of x. So if f of x is the square root of x, what is a going to be? Sorry. So you take a to be 122. So we want to take a point where we know the function well. So you're close. 121. So let's take f of 121 is just 11. So we're taking a equals 11. So if f of x is the square root of x, what is f prime of x? What's the derivative of square root? Yes. Or 1/2 x to the negative 1/2. You're just viewing the square root of x as x to the 1/2. So this is, as was mentioned, 1/2 square roots of x. What would f prime of a be? It would be f prime. Wait a minute, a is not, I think you said 121 by accident. What is f prime of 121? So 1/2 square roots of 121, which is 1/22. So the whole point of the tangent line is everything is really nice at that point A. So stuff nearby, we can approximate it without too much trouble. All right, so now we get y is f of a plus f prime of a x minus a is a good approximation to f of x. And what do we want to take for x? $122. So if x equals 122, f of 122, which is the square root of 122, is approximately f of a is 11 plus f prime of a is going to be 1/22, 122 minus 121, which is 11 and 1/22. So let us switch to Mathematica. Let's say square brackets about the variable, and then you do an underscore. Is this large enough so that everyone can see? Tangent line is 11 plus minus x goes from maybe 110, so go 11 lower to 11 higher. What do you think? That's a pretty good approximation. If I go over a larger region, the approximation is going to start to look bad. It's not the square root function approximating with a straight line. What I can do, these subjects, I really want you to learn. Now what I'm going to do is I'm going to go from 110 minus c. When c equals 0, we're just plotting it as before. What I can now do is I can increase the value of c. C over larger and larger region. Even going up between 80 and 160, it's not so bad. But all the way up to 40, my value, which is really effectively 50. We can see it's okay. It's off by 1 or so. We're getting to get off, but it's not horrible over such a large region. Now, when you are plotting things, sometimes a better thing to plot is rather than plotting the two functions, what could I plot? Put this back over here. Instead of plotting the two functions, it might be better to plot the difference. So let's plot f of x minus this whole thing. And so now, depending on the range I'm looking at, especially on the small range, you can see the scale of the error. And this is really valuable in terms of zooming in. So let's see numerically how close they are. Let's take the numerical value, square root of 2, let's say 5. Let's take the numerical value 11 plus 1. Go a little bit further. Okay, so I'm seeing rounding errors, but not by that much. And then you could try to do a little bit of an estimate. How much is the error? This looks really good. We've got the square root of 122 as a nice fraction, and we're off by 0.0009. Actually, 0.0009. 0.0009. Not bad. This gives you a rough sense of the accuracy. It's maybe on the order of like 1/121 squared. So this is the power of the tangent line approximation. We can take these complicated functions and we can approximate them without too much trouble. Right. Any questions about stuff like this? Yes. So C is by parameter that I'm varying. So to manipulate, because the C is outside of the plotting, the C is going to be. So I have my square bracket here, which ends the plot. It then says manipulate with C going from 0 to 1. And in fact, what I could even do is I could even hit the play button, and it would give you like a little movie. As it just kind of see changing, you can just see in real time how it's varying. C is changing how far I'm going to both sides of 121. I'm starting off, technically going off 11 units on both sides. When C equals 0, I'm moving 11 units on both sides. And then as C gets larger, 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 I get further and further. It's changing how much you see. Right. So for instance, if I put C to be 100, you can start to see sizable difference in varying extremes. Right, C ranges from 0. Next one was just plotting the difference. And again, for lots of things, it's far better to plot the differences in the actual values. Just ended with just the values. So this is what's going on in one dimension. So now, not surprisingly, we want to figure out how should we look at things in several variables. So we need to generalize the notion of derivative. So we've talked about the definition of the derivative before. And we see that the generalization comes from looking at in one variable, the function, subtracting the tangent line approximation, and saying that this is so good that even when we divide by how much we move by, it still tends to 0. So we need to figure out how do we generalize this. And if you think about this, we've seen stuff like this before. We took a line in one variable where you have the slope, which is a real number, and we generalized it to several variables where the slope became a slope vector. And so what we're going to do now is the derivative is going to be a vector. And the derivative of f is going to be partial f, partial x1, partial f, partial xn, if f is a function with n inputs and 1 output. So f takes n inputs, maybe it's 3 variables, maybe it's x, y, and z. So one example might be, the derivative of f might be df dx, df dy, df dz. And other notation for this is you sometimes write triangles f or grad f for gradient. To some extent, the more names something has, the more important it is. You've done statistics. Who has done some statistics? Have you heard of the bell curve? Have you heard of the Gaussian? Have you heard of the moon? And they're really all the same. It's just 3 different ways we refer to the same thing. we have lots of different notation for the derivative. Note it is a vector. So now that we have a vector, the question is, how can we use this vector? Think about what's going on. In one dimension, what is the derivative telling us? It's telling us how much do we change. So if the derivative is positive, as time passes, I'm getting a little bit larger. And if I go backwards in time, I'm getting a little bit smaller. If the derivative was negative, then as time passes, I'm getting a little bit smaller. So the sign of the derivative tells you whether it's increasing or decreasing. Similarly, the components here tell us, are we increasing or decreasing if we move just in that direction. And then if I want to move more generally, so if I start off at my point here, let's say it's A1, A2, and I have some new point here, XY. Maybe instead of A1, A2, maybe I'll change notation. And call it X naught, Y naught. How can I get from X naught, Y naught to XY? There's infinitely many ways I can do it. Somebody give me a nice way to do it. So that's one possibility. Absolutely one possibility. I won't do that, but that's one possibility. Yes. Yes. What's interesting is almost surely that is what people would say. But could you say what people won't? Oh, no, 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 no. This is like Monty Python. 5 is right. Yes. There's something very similar to what was just suggested. Going horizontally. Yeah, you could go up and into the back. No one does that. We always go horizontal first and then vertical. It doesn't matter. No, but just for a lot of things, this seems to be the convention. We move horizontally and then vertically. Why? Well, the X comes before the Y. If we do that, we could do lots of different paths. And the idea is to try to take into account what kind of changes do we have. So we could look at that. We could go this way as well. And what we could do is we could try to see how is the function changing as we move over different ways. So what is my change? So the change in X is X minus X naught. The change in Y is Y minus Y naught. How much should the function change if I move along the X direction? So how do you guess, how much would you say the function should change? Because if we move in the X direction, there's no Y, we're just moving in the X direction. So if we just move in the X direction, what should the change in the function be? So let's write the tangent line in X direction. Tangent line in the X direction should be f of xy is f of x naught y naught plus what? Okay, partial derivative of f with respect to x and what is that? Where will we evaluate? At x, no, not at x. where are we evaluating? Where do we start? We have a function of two variables. What at x naught, y naught. So we evaluate the derivative at x naught, y naught, and now we multiply by the change in x, which is x minus x. But you have to remember, even though y is not changing, it's still a 1 for the y. And so really, I'm writing f of x, y, but it's really f of x, y naught, because I haven't really changed the value of y. If I do the tangent line in the y direction, that'd be f of x naught y, I'm keeping x fixed, it would be f of x naught y naught plus df dy at x naught y naught times y minus y naught. And that would be how much we change if we just look at the y direction. And so the tangent plane becomes f of xy is approximately f of x naught y naught plus df dx x naught y naught x minus x naught plus df dy x naught y naught y minus y naught. Let's look at this. Let's make this a little bit clearer that this is a tangent plane approximation. Let's let z be f of xy. So think of it as I have the xy plane, and z tells me how high it might be. It's the value of my function. If you want, think of it as what is the temperature of the point xy? Okay. And we want to try to find the equation of the tangent plane. And it should be, z would be z naught plus df dx at x naught y naught x minus x naught plus df dy x naught y naught times y minus y naught. And of course, z naught is just the initial point f of x. So I love Rubik's cubes. And at some point during the semester, I'm happy to do a Rubik's cube tutorial. It takes about an hour to learn how to do a 2x2 cube. So I happen to have this cube in my bag. Somebody was talking about this earlier before class. This is called a mirror cube. Does this look similar to a 3x3 cube? Yeah. What's the big differences? Yes. What is that? Good. They have different, the pieces have different size. What else is different between this and the regular cube? Yeah, it's all one color. So if you learn how to do Rubik's cube by first solving the red side, well, all the sides now have the same color. As you start to turn it, it actually becomes a three-dimensional explosion. It turns out that the way to solve this cube is the same as solving a regular 3x3 cube. You have to use now size rather than color. To me, it's much easier to look at, say, red, green. So I can see that much more easily than some of these pieces look very similar in size. And it does take me more time to solve a cube like this than it does to take me to do a regular cube. But it's the same mathematics. It all comes down to, can you recognize what you need to do? Most of the material I teach you, and this is being recorded, you will never use in your life. That doesn't mean it's not worth knowing. Every now and then you might need to use it. It's good to at least know it exists so you know what to look up. I've had numerous graduates tell me years later, you were right. I really didn't use most of the stuff. Every now and then, something's come up and it's good that I knew what to look for. So much of what you're doing in math is pattern recognition. We need to find the gradient, the derivative. What is the derivative of f? So what will be the gradient of f? Just in general, how would you define it generally? What was that definition of the gradient? It's a vector. What are the components of the vector? Right, the partial derivative with respect to x, point x naught, y naught, the partial derivative with respect to y, and x naught, y naught. Do you recognize that in what we have above? Do you see the gradient? Well, the gradient's a vector. I don't see any vectors that I can see. So how is the gradient coming into play? Gradient coming into play. Write this really pedantically. Gradient of f. Remind us of it. Times with plus. You're close. It should involve something involving x minus x naught and y minus y naught. But if I just add them, what kind of operation can I do with a vector to get it done? I could do the length. What else could I do? Dot product. Can you see anything that might be worth taking the dot product that involves x minus x naught and y minus y? What would be a good thing to take the dot product with the gradient?
X minus x naught.
Yeah. So this over here, switch to red. This is the gradient. And this is the change in notation. Notice how similar this is to what we had before. In one dimension, we had, where do we start? That's the z naught. And then we added the instantaneous speed times the elapsed time. And now what we're doing is we're approximating that, and this is how we get our equation of length. Is that if I start off at z naught, which is x naught, y naught, and I move in one direction, that's a line. If I move in another direction, it's a line. Two lines give me the equation of length. And so this is going to give me a relationship that is linear in z. So this is going to give me something like here. Z equals z naught plus a x minus x naught plus b y minus y naught. So after some algebra, you would get alpha x plus beta y plus z sec. When the dust settles, you're going to just get some linear relationship involving x, y, and z. That's the equation of the plane. Because once I specify x and y, z is uniquely determined. So a plane should have two free variables. I have my two free variables. And now I have my tangent approximation. So we can now approximate complicated functions of two variables just by knowing what's going on with functions of one variable. We just essentially generalize this. What makes things more complicated now is that the change is a vector, it's not. But we've seen this before. If we saw this with the equation of a line. The equation of a line, we start off with the slope as a number. And then we said, well, slope as a number, no. Let's look at slope as a vector. And now we do the exact same thing. When in doubt, always try to reduce to a case you already know. If we take a special case when there's no change in y, it's got to reduce down to the tangent line x, and this does. If we take the case when there's no change in x, it has to reduce to the tangent line in y, and it does. This is the natural generalization. And this allows us to approximate complicated functions at a real point where we understand this. And so I could give you now a more complicated relation involving x and y, and we can play the same game as before. there have been some questions in your email about I talk a little bit more about tangent planes and tangent plane approximations and how you find them. If this is not sufficient, please let me know. I speak Klingon. I do a little bit of Klingon. I try to do that. Enhancing young children. Eventually find some teams for one of the people learned just enough Klingon to say no to young Sheldon because he was annoying, and she figured if she spoke to him in Klingon, he would at least appreciate it. This is incredibly powerful. It's a generalization of something we've seen before. It's easy to use. It's not the best approximation possible. What do you think might do a better job than just using the first derivative? What do you think might do a better job than just using the first derivative? Second derivative, right? This is where things start to get very complicated. I start off with a function. The first derivative is a vector. Now I have to take the derivative of that. It turns out the derivative of that's going to become a matrix. And it just starts getting worse and worse the further you go. And at some point, you just have mathematical formulas that you just. So it's nice in one dimension because you start off with a function. Its derivative is also still just a number. The derivative of a derivative is also still just a number. You're my physicists. So when you take quantum mechanics, a huge amount of quantum mechanics is how do you quantize a classical system? And there's many ways of doing this. And sometimes what you do is you do the basic because you symmetrize things. So you might do xp plus px because you no longer have commutativity. Things get more complicated as we go further down. But this is your great start. This is the definition of the tangent plane combinations. Okay. So the next is then trying to do some rules for differentiation. So rules for derivatives. So essentially, when in doubt, always go back to what we know in one dimension. Whatever is true in one dimension should generalize to higher. So if I give you f of x, g of x, no, let's start. Let's do the f of x plus g of x. Its derivative is f prime of x plus g prime of x. The derivative of a sum is the sum of the derivatives. The same is true if I take the derivative of f and g, and now I'm going to just use x with an arrow to mean x1 through xn to just tell me that I'm dealing with a function. So I just save to my list. X1, x2, x. So the derivative of the sum would be the derivative of f and x plus the derivative of g. And the proof is really the same. Because it's a sum, when you do all the calculations and all the limits, it follows the same way. Similarly, for the derivative of f of x minus g of x, and the derivative of c times f of x. That's just going to be c times the derivative of f. This would just be the derivative of f minus the derivative of g. So these are the easy ones. What is the first complicated rule of derivative that I'm going to discuss? Product. So if I give you f of x times g of x, its derivative is f of x to f prime of x times g of x plus f of x g prime of x. What do you think the derivative of f of x g of x should be? If life were good, what would it be? What would you call it? Yeah, it would just be the same thing. It would be the derivative of f times g of x plus f of x times the derivative of g of x. Are we allowed to do this? Is this legal? What kind of object are these? Object is df and dg. Vectors. And what kind of object is g of x and f of x? Not constants. Yes. Because as x varies, they could vary. What kind of object is the matrix? It's a function, but what kind of function? Or what's the output? Where does it live? Is it a vector? Sorry? It's just an f of x and g of x. It's just a number. So f of x and g of x, these are just numbers. We have f and g take, say, n inputs and give you one output. But the gradient of f and the gradient of g, the derivatives, they take n inputs and give you an output. So this is a vector, this is a table. Can you multiply a vector by anything? Is that operation allowed? If I have a vector, if I multiply a vector by 3, what does that do? It multiplies each element by 3. So we can define a vector and a number combined absolutely fine. So there is no problem here in this definition and this works. And you would prove this very similar to the standard proof of the derivative. What you could do is you could even just do it component by component. Do component by component. Take the derivative with respect to, say, the kth variable of f of x, g of x. And you would get, it would be the derivative of f with respect to the kth component times g of x plus f times the derivative of g with respect to the kth component. And that would be the kth component of the derivative of the product. And then you just put everything together. Okay. So the product rule is actually not that bad. Building on a successful product. Yes. Quotient. Are you a little bit worried with the quotient rule? Yeah, because this is a division, so maybe the quotient is a little bit worse. The quotient rule is if I give you f of x over g of x, its derivative is f prime of x, g of x, minus f of x, g prime of x, over g of x squared. So what would you guess if the world were nice for the derivative of f of x over g of x? Just the same thing. Derivative of f times g of x minus f times the derivative of g over g of x squared. Are we allowed to do g of x squared? What kind of quantity is g of x squared? What kind of quantity is this? It's just a number. So actually the quotient rule is proved the exact same way as the quotient rule. There's nothing we need to worry about because we have a g of x squared down below. If we had a g prime squared below, completely different story. And so in the proof, same as product, do d by d xk of f of x g of x. And you just do it for each component and and then you put all the lists. Okay. So let's do some examples. So let's say I give you f of x is x squared y cubed z to the fourth. Is there a question? Yes? Yeah. Yep. So let's say f of x, y, z is x squared y cubed z to the fourth. And let's say g of x is going to be x, y, z. I want to find the derivative of f of x over g of x. So what formula should I use? You forgot my favorite New England transcendentalist. Simplify, simplify, well, hey, simplify, 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 simplify. You should always think about simplifying before you do any calculation. We could do this with the quotient rule. And in fact, this is a great way to check and see if we understand the quotient, because we can also do it without the quotient rule. So if we try to do this without the quotient rule, how could we write this? What is f of x divided by g of x? X, y squared z cubed. So now, if I want to calculate the derivative, I take the derivative of the first piece with respect to x. What is the derivative of the first piece? What's the derivative with respect to x? Y squared z to the third. Now, for the second component, I take the derivative with respect to y. What's the derivative with respect to y? 2xy z to the third. And then the last respect to 3xy squared z squared. Now, the derivative of f of x over g of x, I can also write this as the derivative of f at x times g of x minus f of x times the derivative of g at x over g of x squared. All right, so now let's do this the long way. So first we have to calculate what's the derivative of f. So that's going to be a vector. What's the derivative of f? We have x squared y cubed z to the fourth. So what would the derivative of that be? So first I have to take the derivative with respect to x. So we have spoken as a chance. What's the derivative of x squared y cubed z to the fourth with respect to x? Okay, 2xy cubed z to the fourth, then the derivative with respect to y would be 3x squared y squared z to the fourth, and then with respect to z would be 4x squared y cubed z cubed. We multiply this by g of x, which is x, y, z. Right? Then we subtract f of x, which is x squared y cubed z to the fourth, and we multiply that by the derivative of g. What's the derivative of g? And then we have to divide by g of x squared, which is x squared, y squared, z squared. Show the same y function. And when you look at it, it's not immediately clear that these two are going to be the same. Let's look at just one component. For the first component, we have 2x y cubed z to the 4th times x y z. So we're going to have a 2x squared y to the 4th z to the 5th, right? Minus, we'll have x squared y to the 4th z to the 5th over x squared y squared z squared dot 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 dot. And so for the first one, we have x squared y to the 4th z to the 5th over x squared y squared z squared. So the x squared cancels, and it should be y squared z cubed. So I'm not doing all the algebra, I'm just doing the first one. This is enough to show that it works. For this problem, there's nothing wrong with doing it using the quotient. And in general, you're not going to have something that's going to simplify nicely. Why did we have something that simplified so nicely? Yeah, I chose this. I'm the one at the blackboard. If I can still call it the blackboard, projecting to a swing wedding in town. Why would I choose something like this that's so nice? Because I'm doing the calculation, right? I'm not going to choose a really painful problem for me to do. I'm not going to do one. But also, this way you can check and see, here is evidence that supports my theory that this really is how you get to it. Have we talked about the fundamental game of calculus yet? Areas of the curve. Okay, so later we will prove the fundamental game of calculus. You don't get the title fundamental lightly. And it's often not proved in high school. It's not that bad. So we will discuss the proof in detail, and we'll go through the proof in detail. But when you're done, you test and see if it's right. Well, you need shapes where you can find the area under the curve. What's the first shape you can think of where you can calculate the area nicely? So what's a shape where you can calculate the area easily? A rectangle. So that would be the function f of x equals c. All right. The fundamental theorem of calculus works for a rectangle. What's the next simple shape? Triangle. F of x equals x. Great. So we've now verified the fundamental theorem of calculus for rectangles and triangles. There are easier ways to calculate the areas of rectangles and triangles than using the fundamental theorem of calculus. So the first non-trivial shape is what? F of x equals x squared, parabola. And so we use the fundamental theorem of calculus and calculate the area under the parabola. And then, right? Does anybody know the area under a parabola? So how do you tell if it's correct? You could actually do a shape other than a parabola. Depending on how good your school is. What two-dimensional region would be the area? The circle. So you could do maybe the square root of 1 minus x squared, and that would be a good non-trivial test. Or we have to find another way of calculating the area of the parabola to show that this works. So I chose this example deliberately so that we could see everything is nice. Right, this is a good place to start.